Welcome back. In the last session we covered problem number 7. Now let's see problem number 8. The circuit showed in figure, transistor M1 is in saturation and has transconductance GM is equal to 0.01 Siemens, which is ampere per volt. Ignoring internal parasitic capacitances and assuming the channel length modulation lambda to be 0, there is no channel length modulation, and small signal input pole frequency is input pole frequency is the circuit is this is 5 kilo ohm, this is V in, VDD, and this is 1 kilo ohm, and this is what is your 50 picofarad. Okay. Now this is what is the circuit, and then asking for input pole frequency. What is input pole frequency? Okay, I'll tell you that. Saying that neglect MOSFET internal capacitances. Actually, it is having gate to source. Strictly speaking, the bulk is connected to ground. Gate to bulk capacitance is there. Saying that you can ignore those capacitances. Drain to source capacitance. That is because of reverse bias P injection rate what you have at the drain, and the Miller capacitance which is due to overlap. That all those things can be ignored. That's what he told. Only the 50 picofarad cap, which is what is present in between input to output, this is what people call it as Miller cap. This is what people call as Miller cap. That Miller cap, if that is what is coming here, then the resistor and the Miller effective cap at the input, whatever you are going to get, that is what is going to give you a low pass filter, which is what is going to give you a pole. That is what we need to get it. Therefore, if you ask me equivalently after applying Miller effect, if I write the circuit something like this, this is what your capacitor, let us say C1, and you will get C2 due to Miller effect. Then this is what your resistor, which is 5 kilo ohm. Then this is what is your 1 kilo ohm. This is what your V0, and this is your VDD. If you consider this, and this is what your VI, this is what is going to fall. And if you ignore the device internal caps and then overlap cap and all those things, at the input, this is what is forming a pole. This is what is forming a pole. And then what is the pole frequency? 1 by 2 pi R into the C, what I told, C1. Therefore, 1 by 2 pi R is already there, which is 5 kilo ohm, and C1, if you know C1, you will get the answer. This is what is our input pole. Right? How to get the C1? If you ask me what is Miller's theorem, the Miller's theorem is if you have a system which is having a gain of A, and if there is a Miller impedance Z, this is what your Vi and this is what your V0. A is nothing but V0 by Vi. A is V0 by Vi. Then using Miller's theorem, we can resolve the feedback or output to input impedance both at input as well as output. This is what is Z1, where Z1 is equal to Z divided by 1 minus A, and this is what is your V0, and then Vi, this is nothing but your Z2 is nothing but Z divided by 1 minus 1 by A. This is what is Miller's theorem. Similarly, if you apply Miller's theorem, the capacitor, whatever you have, let us say Z is nothing but what? Here Z is nothing but 1 by SC. Then what is your Z1? Therefore, what is your Z1, which is what is the input component? that is nothing but Z divided by 1 minus 1 by A. Therefore, Z divided by 1 minus A. First of all, what is voltage gain of your common source amplifier? Voltage gain of your common source amplifier is nothing but, therefore that is common source amplifier. What is your voltage gain? Voltage gain, just I think just before this within the problem, minus Gm into Rd dash. What is Rd dash? Minus Gm into your transistor resistance, which is small Rd, in parallel to the load Rd what you have. But he told that what is your small Rd? If you neglect channel length modulation is 0, then your small Rd is equal to 1 by lambda Id. When lambda is 0, then small Rd is infinity. Neglecting channel length modulation, then it is simply minus Gm into the load what you have. Therefore, what is that? What is Gm? Gm is already given, which is 10 milli into what is Rd? That is 1K. Then your gain is nothing but minus 10. Therefore, your gain of common source amplifier is nothing but minus 10. Then if you use that, what is your Z1? Your Z1 is equal to Z divided by 1 minus of minus 10, 11. But what is Z? 1 by SC. Then 1 by SC into 11. This is nothing but 1 by SC into 11C. That is what it is. Therefore, effectively, this is what people call it as effectively 1 by S into C star. Therefore, C star is nothing but C1. This is nothing but your C1 which we represented. This is nothing but your C1 which we represented. Effective capacitance. That effective capacitance is equal to 11C. Therefore, 11 into what is your feedback capacitor? 50 picofarad. Therefore, you will get 550 picofarad. Then, if you calculate your input pole, if you calculate your input pole here, therefore, input pole is equal to 1 by 2 pi or 5K into 550, that pico will become 10 to the power of 12. After calculating it, what you get? 57.87 kilohertz. 57.87 kilohertz. This is what is the answer. Okay, only calculations. You need to apply Miller's theorem. Once you apply Miller's theorem, you will get it. Okay. Whatever Miller capacitor which is 50 picofarad, but it is not 50 picofarad equivalently represented at the input. That equivalent represently nothing but 550 picofarad, means 11 times of your Miller cap between input to output cap is represented equivalently as 550, means 11 times of Miller cap is represented at the input, due to which whatever pole you get, input pole, that is what is represented. Okay, take it. Then we'll solve problem number 9. I'll give you one more minute. After that, we will see problem number 9. I already derived the Miller's theorem, if you remember, in op amp, right? Chapter number 4, Z1 and Z2. I already derived these two. Why we got Z1 is equal to Z by 1 minus A, and then Z2 is Z divided by 1 minus 1 by A. This we already solved. Done? Okay. Now problem number 9. What is the voltage V out in the following circuit? Okay. This is some 10 kilo ohm. If you observe clearly, can I write equivalently? If there is no, what do you call, resistor, then it is simply inverter. This is what your V in and then V out. This is what your V out and this is V in. But remember, there is a resistor from output to input. Again, this is what is called Miller resistor. What out may be, there is a resistor. This is what is our resistor, which is 10 kilo ohm. But if you observe clearly, what it may be, irrespective of the resistance value. What is the current which is what is flowing through it? What is the current which is what is flowing through the 10 kilo ohm? The current which is, let us say there is some current, then that current has to go through PMOS gate, NMOS gate. Current entering into your gates. Current entering into your gates. This is what is 0 ampere and here also 0 ampere. Surely here also 0 ampere. If there is no drop across 10 kilo ohm, then whatever voltage you have, the same voltage you get here. What does it mean? Equivalently, this can be represented something like this. This is nothing but equivalently. Even though there is a resistor, it is like short. Your V out is equal to your V in. And I already told, if you take only CMOS inverter, this is what is your V in and this is what your V out. We have transfer curve and when you have V out is equal to V in. Your V out is equal to V in. This is nothing but your V out is equal to V in short. V out is equal to V in short. Then the intersection point is the solution. That is nothing but a switching point. Let us say VDD by 2, if it is symmetrical CMOS inverter, VDD by 2, else that is nothing but a switching point. Okay, this is what it is. Therefore, what is the output? I already told you, right? Input is 1, output is 0, input is 0, output is 1. When input is VDD by 2, output is VDD by 2. That is nothing but a switching point. When both are equal, that is nothing but a switching point. Answer is C, switching threshold of inverter. This is what your switching threshold. Therefore, answer is this is what is switching threshold or switching point. In digital, when V in is equal to V out, that is what your switching point. Okay. If it is symmetrical CMOS inverter, the switching point will be VDD by 2. Power supply, highest power supply by lowest power supply by 2. That is what your switching point. Now, problem number 10. A long channel NMOS transistor is biased in linear region. Okay, this is what is biased in linear region. Okay, linear region. Fine. With VDS is equal to 50 millivolt. With VDS is equal to 50 millivolt, and it is used as a resistance. Yes, this can be equal to represented as a resistance. Okay, RD linear. Okay, between drain and source. That is known to us. If the transistor is in linear region, that is nothing but a resistor. Which one of the following statements is correct? Okay, first of all, what is your RD linear? When the transistor is in linear region, what is your RD linear? We already solved it. 1 divided by mu n Cox W by L into VGS minus VT. This is what it is. Okay, now let's see. If the device width is increased, resistance decreases. Let's see. Option A. If W increases, if width is increasing, more strength, then your RD decreases. Resistance is lesser. Yes, that is true. That is true. Option B. This is true. Option B is asking not correct. Okay. If threshold voltage is reduced, VT decreases, internally strength is more, your RD will decrease, but it is also decreasing. Okay. This is also true. Option C. If device length is increased, your resistance will increase actually. Yes, this is also true. If L is increasing, length is increasing means resistance will increase. That is fine. Option D. From this also you can say L is increasing, resistance will increase. Option D. If VGS increases, again strength increases, then your channel conductivity increases, resistance decreases. But he is saying that resistance increases. This is wrong actually. Therefore answer is D. Why? If VGS increases, more strength, more conductivity, lesser resistance. But he is saying that more resistance. That is wrong. Okay. Answer is D. Now problem number 11. This is theoretical problem, right? Now the drain current of a MOSFET in saturation. The drain current of a MOSFET in saturation. This is drain, source, gate. Therefore ID is equal to, given, which is nothing but K into VGS minus VT whole square. K is nothing but mu n charge W by 2L. That's fine. Where K is constant. Magnitude transconductance. What is transconductance? Differentiation of ID with respect to VGS when VDS is constant. Anyway, this is independent of VDS, therefore no channel length modulation. What it may be? When you differentiate this, 2 into K into VGS minus VT, right? Therefore, what is the answer? 2 into K into VGS minus VT. That is nothing but answer is B. I think we have seen this already. This is theoretical. Okay, straightforward. When you differentiate, you will get it. 2 into K into VGS minus VT. Where K is nothing but mu n CX W by 2L. 2 will be cancelled. Therefore, mu n CX W by L into VGS minus VT. That is what is your GM. That is known to you for voltage bias. Okay. After this, we will solve the last one, which is the 12th problem. Then after that, I can say the student workbook problems level 2 are also over. Okay. I'll give you 1 minute time. Then we will see the last one, 12th problem. Write down the last one, 12th problem. The drain of n-channel MOSFET is shorted to gate so that VGS is equal to VDS. This is what it is, okay? This is drain, gate, source. The threshold voltage is 1 volt. VT is equal to 1 volt. If the drain current is 1 milliampere, when ID is equal to 1 milliampere, for VGS is equal to 2, for VGS is equal to 2 volt. Then for VGS is equal to 3 volt, what is your ID? Okay. I already told, when gate and drain are connected and if VGS is greater than or equal to VT, this is what is called diode connector transistor. This is always in saturation, provided your VGS is greater than or equal to VT. Because he told that VGS is 2, surely greater than or equal to VT, then ID is equal to 1 milliampere. That is what, right? Therefore, there is ID. This is what is having ID with respect to VGS, right? Now we need to get it. Therefore, now we know that when the transistor is in saturation, ID is equal to Kn by 2 into VGS minus VT whole square. Okay. Then what I do, you know already, let me call this as ID1 VGS1, ID2 VGS2. Okay. Then if I do ID2 divided by ID1, because I want to find ID2, Kn will be cancelled, then it is VGS2 minus VT divided by VGS1 minus VT whole square. You will get it, right? Therefore, what is VGS2, which is already known to you? 3. What is VT, which is known to you? 1 divided by VGS1 2 and VT 1 whole square. 3 minus 1 2, 2 square 4. Therefore, what is your ID2? Your ID2 is equal to 4 into ID1, and ID1 is also known to you, which is nothing but 1 milliampere. Therefore, it is 4 milliampere. If you observe clearly, when VGS is increasing from 2 to 3, which is nothing but delta is 1 volt, but the change in ID is not linear. It's not 1 milliampere increment. This is nothing but 4 milliampere increment. That is because of what? Even the delta VGS is 1, but the delta ID is not 1. That is because it is non-linear. Because this is what is non-linear. That's fine. Therefore, what is the answer? 4 milliampere. Answer is D. With this, I can say the student workbook problems level 2 are over. Then we will see remaining sessions. Okay. I think you please continue. I'll sign off for this session. We'll continue in the next session. Okay. Thank you.